Yeah, go ahead and check that. Oh, yeah, check that binder real quick towards the very back. Yes, ma'am. No, I did not. Not yet. I meant to do it this morning and then I got distracted. It's my next on the grading to do though. Yeah.
Would it be okay if I came in after like early release like with lock to finish up mine? Okay.
Today or tomorrow?
Tomorrow. Will you be in this room?
Either here or the workroom.
Or okay.
It got fixed this morning. Thanks, Bob. All right. So, goals for today. We are very talkative today. Goals for today.
30.
Goals for today. Guesses. Then I want to finish the 7.4 notes, do the 7.5 notes. If we have any extra time at the end of class, that'll be on problem sets. That being said, the notes took a little bit longer than I intended them to, so I'm going to try to preserve some time moving forward as far as like the beginning of class to work on that problem set. I also have a proposal for how I would like to do the Unit 7 test. You will probably like the proposal. So we'll talk about it later. All right.
Yeah.
Can I like look at the 16?
What?
That's cheating.
What servings per?
You can try. I can't see it.
60.
All right.
156.
You there?
You don't say 145. I was thinking 64. 60. Alright, there we go.
21? I haven't made the class quite as mad lately, so I appreciate it.
You should get the measurement of the box. You should get the measurement of the box because it doesn't look up to scale. Yeah, I don't want 43.
Oh, 32. Yeah, go on.
$1. That's $100.
40.
Don't answer any which I did. How many times have I said it already? 60.
38.
You're not a human being.
Alright, bro.
It's okay, my boss tells me that he forgets that I exist. Like actually.
Second, did you have a guess?
60.
60?
Yeah.
All right, anywhere else? No. 38.
Hi.
John?
59.
69?
Anyone else? All right, are you ready?
We need a count by count.
Video reveal.
Okay. That's so tiny.
Oh, there's sound. I didn't have my sound on yesterday.
It looks like a race box. 30, 60. There's no way to 60. Just like at least 30 or 20.
He color coordinates them too.
Oh. It's not economical, bro. I told you, it's not economical. 34,
we're 2 away.
Yeah.
Honor said 38.
Yeah, I said
38.
38. Yeah, we got
I told you, but we're
Yeah.
not.
Oh, it was 30. Let's go.
Wait, I'm a notable,
by the way.
I'm a notable mention because my numbers are flipped backwards.
Alright, cool. So what I need from you guys, OPS. It's our favorite guy. Anyone know who this is?
Oh, that one dude.
That one
George
dude.
Friedrich Bernhard Riemann.
Oh,
Riemann.
Riemann. That's what AB learned today. Alright, what I need from you guys. Wow. We actually need to catch up a little bit. We are behind my other class. So I owe you some shell method stuff. This is my second block, so I owe you some shell method. We did shell method in terms of X last time. We did not go in terms of Y. So we need to do that. So I need you to find 7.4. I'll go to the top so you can see what it looks like. I need you to find shell method 7.4. We're going to roll through some of this, then we'll take a break and we'll roll through 7.5. 7.5 is really easy, so I'll go kind of fast through that. Yeah. Mhm. Yeah. Will you give it to me at the end of class so I don't lose it? All right. Yeah. Yeah.
And then can I come early Thursday?
Yeah.
Oh, it's supposed to. That's so weird.
Oh, that's just like college. It's just like college science classes. They all do that. When you're like, I got a 65. All right. So just to kind of review what we did last class, with shell method, I'm just gonna start talking. So you guys can decide if you want to pay attention or not. If you want to talk, don't be in here. So shell method. What we did last class was we found a way to rotate parallel to the axis we were working with. This could be beneficial, like the questions we did on the bottom, if we need to work in terms of X, but we're going around a vertical line. When we had been doing disc and washer before, because of the horizontal orientation of that radius, we were going to have to work in terms of Y, so this gave us another option. The height was relatively usual because that was in our region. We just did a top minus bottom. So you see this kind of X minus X cubed minus 0. That was consistent the entire time. Our big focus was that radius. The radius was working with a top minus bottom with our variable of integration. So in these ones, X and our axis of rotation, the ones we're going to do in a second will be in terms of Y. The one we're going to do now is a little bit different. This one I could certainly do in terms of X using washer or disc method, but it might be a little impractical. What I mean by that is the first line we're going to go around, let's get some colors going, is this line right here. If we were going to do disc and washer, does anyone see kind of an issue here if we were going to orient our lines like this for our discs? For our washers, in this case, all discs. The big issue I see, what's up? Yeah, did you ever notice at X equals 2, there's like a very strong shift in what function is controlling the kind of top of that radius there. We go from this parabola to this line. What that would mean would be a very inconvenient need for 2 integrals here. So while that's doable, a shell method might be more advantageous. So we're going to try that. This is a good option if you would like. Now, my pen is too thin. I want it to be prettier. Struggles. Same, bro. All right, so I'm going to rotate parallel to my axis. I'm just drawing this line anywhere I want in the region. This is going to represent my height. because I'm going to be rotating like this. So here's kind of a representative shell here. And my radius would be right there. So we're going to try to write our shell method area formula. Then we'll transpose that into our volume integral. Yeah, what was that area formula for our shell? Nina. Nina's right that we have a 2. There's a pi. And what other things? RH. All right. So here, since we're kind of rotating parallel to this axis, everything's kind of happening horizontally. Notice that H is horizontal there. So if we've got that horizontal H, we're going to be working in terms of Y. Another key that we might want to work in terms of Y, look at that function. How often do we get functions that are X equals stuff with Y's in it? Not very often. So even this question writer is like, hey, you thought about working in terms of Y? You might want to. All right, let's do the height first. Anyone think they know the top minus bottom for the height? So this dot minus that dot. We're going this way, this way. All right, I like 7 minus. That guy's on the curve though, so he's going to change a little bit. Square root of y. We want to use our function here. It's already in terms of y. I might have to solve for it, but here we got that in terms of y. So 7 minus the square root of y. All right, thinking back to how we found the radius last time, anyone think they know the radius here? Let's look back at some of these radiuses. X minus 0, x minus negative 1, or x plus 1. 2 minus x. All right, I like y minus, what did you say? 0. Perfect. What we're doing is we're taking our variable of integration, which in this case is y, and we're going down to the axis of rotation. Remember, these shells are kind of layering on top of each other, so that y represents at whatever y I am in the bounds, that's how far up I am. So this y is kind of the height of the current shell, and the 0 is the x-axis that we're going back down to. So this distance right here is our y. All right. So kind of the bounds are going to take that y from 0 all the way up to the top bound. So it's going to change depending on where we are kind of in our bounds in our integration. So if you think about kind of what's happening is we're taking these, remember how we kind of talked about them as soup can labels? We're kind of layering a bunch of them on top of each other, and that y is going to take all of the layers from y equals 0 up to that top bound. So it's going to keep layering on top. All right, I'm going to pull that 2 pi out in front of the integral. I'm going to simplify a little bit. So I've got y, 7 minus the square root of y. My differential is now dy. Now, I was saying a little bit about the bounds to Nina. Anyone think they know what the bounds will be? 0 to 4. Good. Those are region specific. So we're looking at the region that I graphed in the XY plane. We're going from bottom to top because we're talking about y. So from y equals 0 up to 4. Again, you can use that pencil trick. Stick your pencil on the H that you drew, that height, slide it up and down within your region. All right. Ma'am.
Okay, so let's say like the bottom line is at 1 instead of 0. Would for the
Exactly. Yep. And here's another what if. Let's move that line down to y equals negative 3. Ma'am. What if? Yes, but we would be oriented in this direction going around a vertical line. Yep, so you'd be going right minus left there. All right, so let's do another set of what ifs, because while I love this table's what if of what if it was at y equals 1, that one's in our region. We normally don't rotate around a line that's in our region, so let's pull it even lower. I'm going to kind of go down here. I know it's not really to scale, but I'm trying. All right. Is that radius, as I draw it, is that radius, if I move the line from the pink line down to the orange line, is my radius getting bigger or smaller? Definitely bigger. We're kind of rotating a big guy now. I'm not really going to draw that because it's annoying, but the radius is getting bigger. What were you going to say about the height, Chris? Yeah, the height's really going to stay the same. So one thing we've been noticing about shell method is the height seems also very region specific for this question. So let's do 2 pi r h. Do you guys agree with Chris that the height will be the same? Perfect. So 7 minus square root of y. Thoughts on that radius now? All right, y plus 3. You could do y minus -3 if you're a top minus bottom fan. So your variable of integration minus your axis of rotation. Or if you're a sense-making, picture-making fan, you've got that y distance, and then this is 3 extra right here. So either way to make sense of it is totally cool with me. Thing I'm missing, any extra bound considerations? Or are they the same? They're the same. I'm still working all the way within my region. I want to take shells from y equals 0 up to y equals 4. So I'm going to go there. All right. Yeah. What's that? You don't get the bounds? So we're looking at... Say that again. Agreed. So one thing you might be noticing is we're going to have some space. I know it's not to scale, but we're having some space between kind of the bottom of our region and this axis of rotation. That's the one kind of really cool part about shells is that they already have the hole in the middle. So when I'm plugging in 0 here, that's this first shell that's going around here. We want the radius to be 3, so that's doing the 0 plus 3 there. Is that, am I missing your question and just saying something I'm excited about?
I don't know.
It's okay if the answer is yes.
It's like, how is it, how are
It's around 0 to 4 when the axis of rotation is -3. So like, how does it like stop at from 0 to 4 when we're rotating around
like,
-3?
why wouldn't the bounce be negative?
He's talking about this.
So we don't want any of the shells to be happening in here because we want the hole in the middle, right? So if we took shells where they had a radius of like, if we were going from -3, there would be shells starting right around here. So we'd have stuff and there wouldn't be that hole in there. So what the bottom bound is doing is it's keeping the space between there and there without having any shells. So it's like we skip the shells from -3 up to 0, and then we start so it preserves that hole in the middle. Better? I don't like I guess as an
I
answer.
don't know why there even has to be a hole.
Why there has to be a hole?
Yeah.
Do you agree there's a ton of space between this spot where my region ends and the axis of rotation?
No, yeah, I get that.
Mm-hmm. Do you want me to try to Desmos picture it?
Yeah.
Okay.
First one doesn't-
Keep in mind, if I'm asking, if I seem like I'm sticking on a question, it's because I'm frustrated with myself. I want to be able to answer your question. So don't think I'm frustrated with you, please. Let me get Desmos up. Let's see, we need to rotate horizontally. Ooh, I don't even know if I'm gonna be able to graph this. All right, excuse me, because I'm not going to be able to get that parabola at the front end. This doesn't have the option to put into functions. X equals 7 would be those guys. So we're going to go from 0 to 4. That is not doing what I want at all. This needs to be 4. Is that right? All right, so pretend there's kind of the parabola at the beginning. And here's our -3. So we want, as we rotate this guy, we want to preserve that circle in the middle, that kind of hole in the middle. if we started making some shells on the inside, they would layer up starting at that axis of rotation. So what we're doing by setting the bottom bound at 0 is we're kind of skipping all that space between -3 and 0, so it preserves that hole in the middle. And then we're like, okay, once you get in the region, so from y = 0 up to y = 4, I want to rotate that stuff. Yeah, so it's kind of like I'm keeping the space in the middle and starting the shells when the radius is finally 3. Because there's space. Remember when we were talking with washer and shell about hole or no hole? So if I unplay this and get the perspective back into place where it makes sense, let me drag this around. Notice there's a ton of space between my region and the axis of rotation, so there should be kind of a hole in the middle. And what you're doing by starting the bound at 0 is you're saying, okay, I want that radius to start at 3, so I preserve that space in the middle. I would love to.
The whole unit about is it going to be with
Okay, so it would shade the region all the way down to there. And I know the parabola is not at the beginning, so my apologies on that. It's going to be just like a solid guy. Yeah, so you just need to keep the radius popped up so that there's that hole in the middle.
That's what the first one that we did was look like. Like, except it's not a -3, but it's on the x-axis, but that's what it would look like.
The first one meaning which one? This guy right here?
Yeah.
So the guy we wanted x-axis, so we would want this to be 0. So we would want, oh, not that one, sorry. There's too many things to play here. So we want that hole in the middle, so that's why we start the bound at 0, because we only want to start taking shells when we're in that region. If we push it any lower, you're going to start taking shells that are below that region. Okay, cool. Thank you guys for sticking with me through that. All right. So washer and shell do the same thing, but they rotate in a different way. So you're kind of using the opposite variable. So you can use them a lot of the times, like this question, I could do both of them, but to do washers here, I'd have to go kind of vertically here. So I'd have to work in terms of x, which, like we were talking about at the beginning, would cause me to need 2 different integrals because I have the parabola on the left-hand side and that horizontal line on the right. So while they do the same thing, they find the same volume, you have to use different letters and kind of different thinking. Yeah. So this one, the fact that they're telling me to work in Y is a pretty good indication in this case to work for shell method. Usually for most people, it's going to be a preference about what letter you want to work in. So I know that I have a very strong personal preference to work in X. So I'll try to do that no matter what. Most of the time, I think the AP test is a strong preference for like disc and washer method. So almost every question they give can be done that way. So you just kind of got to do some problems. Your problem set has more rotation problems than everything else because those choices are kind of the hardest. All right, let's keep going. Yeah. What's the perp? What do you mean? No. Yeah. Because there's space between the axis of, like, where the region stops and the axis of rotation. Because then you're not answering the question that they asked. Because I know that I'm supposed to be bounded below by y = 0. They gave me that. They gave me the bottom of my region. So there has to be a hole there because that's like the setup of the problem. All right, so let's do this one. I'm going to move the region up here. So I'm now going to be rotating up here for sake of argument. I can draw the height at a different place if you want, but it's still going to be in the region. Would look like this. All right, even if I drew the height at any different part in the region, do you agree with me? It's still going to be the same top minus bottom. It's still going to be that 7 subtracting that curve, the square root of y. Cool. All right. We've talked a lot about the radius now, so I want to give you guys a chance to figure out before I say it. Whisper to your neighbor as angrily as you can. What do you think the radius is going to be? Because I'm making all the choices for you at the board. The choices are the hard part. All right, is anyone feeling like 100% I know exactly what the radius is? Does anyone want to tell me what they think the radius is? You guys? 4 minus y. Does anyone support that journey there? Perfect. All right, our discussion did something. So here, this distance is 4. The distance between wherever I'm drawing my height and the x-axis is y. So I'm taking that 4 minus y. Or if you're a pattern person, axis of rotation, variable of integration, since my axis is above my region, 4 minus y. All right. Same bounds, different bounds. Same bounds. They're region specific. If you want a pattern, literally all the bounds are region specific. So if you can find a line that's within your region, slide your pencil up and down in that region, whether it's 7.1 or 7.5 that we do today, they all have to do with the region. Yes. All right, if you're wondering about integrability by hand, I could expect you probably to do the first one by hand. It's not going to be super nice, but you're just distributing. The second and third, I probably would not ask you to do that by hand. I can't even imagine the AP test would, because that would be foiling. You'd have a lot of fractional exponents. It would be really gross. All right, just to compare, let's say you're doing this question. I'm going to redraw it because we've had a lot of stuff on the other picture. And all of a sudden, I ask you to rotate around the y-axis. So I'm going from a horizontal line to a vertical line. I could do shell method here, but I'd have the same problem that we were working with before on trying to work in terms of x. If I'm trying to set up this height kind of vertically, I'd have to do 2 different integrals to deal with the 2 different top functions that are going on. So here, in terms of choices, as Jillian started to mention, which method do I choose? For this question, I would be preferential to trying to set up whatever line I'm rotating, whether that be the height for shell method or the radius for our disc and washer. I would be preferential to setting that up horizontally because there's a consistent top function minus bottom function. So here, I would argue that washer method is probably the way to go. Let's review some of those questions we talked about for washer method. The first question I remember was hole or no hole. Thoughts? Hole. I'm not touching that axis pretty much any of the time as I'm going. So I'm going to extend this guy to be my big radius. And here is my small radius. Okay? So if you're imagining, here's your disc with your hole in the middle. I don't like those lines though. They look scary. All right, what was our area formula for disc and washer? What shapes are we using? Pi r squared. We're using circles here. Since I have a hole, I'm going to need 2 of them. All right, big radius. Thoughts? I like it. I love it. So 7, that's that x equals 7 at the end, minus, we're going all the way back to the y-axis, which is x equals 0. All right, let's do the other one. What do we think about the whole radius? Square root of y. Since our lines are going horizontally, again, we had a strong preference for working in y here, so we still want to preserve that square root of y and all the way back to 0. As I'm transitioning to volume, I'm going to factor my pi out. I'm going to simplify. I have 7 squared is 49, square root of y squared is y. So this one would be integrable by hand. I like simplifying because it makes my calculator typing a little bit easier. Thoughts on bounds? 0 to 4. I am still working in the same region. I am still working in terms of y. If you can get those two questions answered, you know the bounds. Yeah. Mhm.
Question where we have to assume that it like flips the terms, so like to get it, if they gave us a term of X, we have to flip it to a term of Y. How do we know when?
So you're going to want to figure out your preference for which letter you're working in. That could be based on what letter you just want to work in. Some of them will work both ways. So a good example of that picture on the side would be a relatively good example of something that could work both ways, because here I could do my radius like this and like this. So kind of that's more of a preference thing. So if you can choose your variable that way, great. I would say the only time you're really going to want to pay attention to how the function is given to you, if you see the function like that, where it's x equals stuff with y's in it, that's a big old hint that you should be working in terms of y. Sometimes they won't do that, but that's kind of your biggest hint to work in terms of y. Ma'am.
So because it says in terms of y, that doesn't tell you
What method?
if it's going to be horizontal or vertical.
No, so that's why drawing your region in the plane is super important, because you kind of have to get an idea of what this looks like. I promise these choices get better the more you practice, and I tried to put a bunch of practice questions on your problem set. If you feel like you need more, I promise I have lots. For the last one, my preference here was really to work in terms of y, so that I could have a consistent kind of right function minus left function here. So to do that for my washer method, I would have to have these oriented horizontally, which for washer method puts me in terms of y. You can kind of look at the orientation of these radiuses in the disk and washer, or your height in the shell method. Whichever way that is oriented is the letter you're going to want to use. So horizontal height, horizontal radius is y, vertical, that's going to be your axis. All right, you guys want to take a break from rotating? All right, if we have time at the end of class, I can come back and do this question. Maybe one more. This one's a good one.
Well-deserved.
All right, one more real quick. This is on the back of that last page. There's a couple other questions in here. This one has kind of all the pieces. So let's look at this one real quick, and I promise I'll shut up. We'll take a break, and then we'll do arc length, which is way easier than this. So we're going to look at the volume of the solid formed by revolving this region, which we're going to talk about in a second. We've got x cubed plus x plus 1, that's your curvy line. Y equals 1, that's the horizontal line underneath. X equals 1, that's that vertical line. Underrated piece of these problems, making sure you know which region you're rotating. Do you guys agree with me that it's going to be this like orange triangle piece? So I'm thinking about, think of those three functions like a fence. You want to take whatever will be enclosed by those three functions. You'll have something, so you'll see the words bounded by, and you want all of those functions to work like a fence. So I don't want down here, because they didn't say bounded by the x-axis. I don't want over here, they didn't say bounded by the y-axis. This is the only part that is fenced in by those three functions. All right. Notice I want to go about the line x equals 2, which is this kind of green line on my paper, but that dotted line on your paper. Now, this is a good example of a question that could be done with disk and washer or with shell. If you're like me and you have a strong preference for working in terms of x, you would want to write this line vertically. Well, that's parallel to my axis of rotation. So if I'm doing that, I would be working with shells. If you don't care, you could do this in terms of disk and washer. You have a consistent top minus bottom with both the large radius and the small radius. You would, since that's going horizontally, have to work in y. This function here, does anyone know how to solve it for x to get x equals stuff with y's in it? I don't. So I think I need to work in terms of x here. So that's kind of going back to that decision-making process. So I'm going to work shell method here. Because not only do I like working in terms of X, but I don't know how to get this in terms of Y. That's a great question. Let's figure it out. We're doing shall. All right, let's start with the height because that's easier. So the height, this line right here. So that height right there. Thoughts on the height? What two things will I be subtracting? I like -1. If it were -0, we'd be going all the way down to the x-axis. Here we want to stop at that horizontal line, y equals 1. That's all right. All right. Thoughts on radius? Thoughts on radius? All right. I like the idea of using 2 at the beginning. 2 minus just x. So your radius is always going to have the variable you're working with and the axis of rotation. So here I'm working in terms of x. So I've got an x there. 2, though, the axis was to the right of my region. So I'm doing 2 minus x, wherever that variable is. All right. Last part, we talked a lot about it. Sounds. Any strong thoughts? 0 to 1 is the claim. Do we like that? Looking, our region goes from x equals 0 over to x equals 1. The reason we're not going all the way to 2 is that's going to be the part that's kind of using, that's going to be the part creating the hole. So we want the last radius we have to be of length 1. So think 2 minus 1. We want that last radius to be away from that axis so we keep that hole there. You're feeling slightly better? Yeah. So not too bad. It'll be nicer because you're only going to be rotating around one line. All right, let's take a brain break. I promise the arc length stuff is way easier than what we just did. More of a formula. Thank you. Say that again. Well, x and then +1 because you're doing x minus -1. All right, take 4. I'm going to pass out some notes. Yes, thank you. To start our next unit. It's my favorite one. The entire year.
Right, but.
You enjoy it? That TikTok is made for you.
Ugh.
It's made for you. Don't forget
I'm so happy.
Oh.
So when you get that, don't have anything for that. And then he's way top. Your level. Your
Was it comfortable teaching like that? Did your niece not hurt?
What?
Did your niece not hurt?
Bro.
Padded chair.
Ashton's looking at the Saturday.
Yeah, just call her out of here. Yeah, really?
Always
All right, so on your desk should be a set of notes for arc length. So no more volume, not even any area. We are going to find the length of something that is curvy. So
We've always done like cloud for it.
yeah,
Is this like new? Have we never done?
that is correct. I will never again teach you something that I've already taught you,
Oh, this is
Nina.
the first one.
We are in
No.
no, technically shell method was, but yeah, we're done. Yeah, Kat, did I miss you? I missed you. I apologize. All right. So we're gonna find the length of something that is curvy. Technically, by the time you do this on an assessment, you're probably gonna have this memorized as a formula. But it's a kind of weird formula. Does anyone mind if I sit down? I am tired. Mostly, I'll kind of window you, Emery. So mostly, the reason I'm showing you how to get this formula is it's kind of weird. So I think you deserve to know where this formula comes from. If you don't feel like writing down like the proof of it though, you do not have to. What I would like you to do is kind of just follow along and make sure I'm not making any weird mistakes. But if you don't want to start going until I get to about here, totally fine. So let's say you're bored one day, you graph something curvy in Desmos, and you do that thing that all my Algebra 1 students do, and you just zoom in like a million times. What's it gonna look like? A straight line. If I zoom in far enough to a curve, it looks straight. I'm gonna kind of take advantage of that to help us find this formula. And one of our favorite Greek dudes. So I'm going to find the length of something that looks like this. Up until this point in your math career, you are not able to find the length of something that is curvy. I'm going to pretend I can zoom in a whole heck ton though. And I'm going to pretend it's pretty close to this straight line. Now, I bet you $1 million that you will not guess the letter that stands for arc length.
Weird key.
Wait, there's 26 people in the
S.
class. There's 26 hold up.
I already gave it away. So that would have been a good guess. That's a weird one. All right. So for some reason they call it S. So I'm going to say that we're zoomed in really close. So I'm going to call this a tiny, tiny infinitesimally small piece of S. dx. So like our differential, it's a little tiny guy. Now, I know everything's easier if I can break things up into x and y components. So I'm going to call this dy and this dx.
The derivative.
It's differentials. What? A little bit, yeah. So thinking of it as like if you talk about vectors in physics, splitting it into x and y components. All right, if you guys ever want time to work on your problem sets, maybe don't talk every single time I stop talking. All right. Would you agree with me and Pythagoras that ds squared equals dx squared plus dy squared? Checks out?
Yeah.
All right. I would like to not know what ds squared. I'm eventually trying to get to this. So first thing I don't like that squared. So I'm gonna square root both sides. Eventually, yeah. I also don't love that I have x's and y's. So I'm going to do something kind of creepy. Technically, by definition, the thing I'm going to write here is true, but it's going to look true based on illegal algebra skills. It'll make sense when I write it. So I'm going to replace dy with something that is equivalent to dy based on definition of what dy is, but will look true no matter what. I'm going to replace it with dy dx times dx. Now, does that look true based on what algebra rules you would envision? All right, technically dy dx is not a fraction. So technically this is true by definition, but it looks true by faulty algebra. All right, it is legal, but the reason you think it's legal is not the reason you think it's legal. Technically, dy is defined as dy dx times. All right. I want to do a couple of things. I want to make both of these squared instead, and I want to replace dy dx with a different way to write a derivative. So let's pretend instead of my function being labeled y, my function was labeled f of x. How do we write the derivative there? F prime. I'm only really replacing this because it's going to look cleaner in my final formula, and that's how most textbooks write it. All right. No, you don't have to write this at all. There's just some good math in it. You guys see anything in common between those two terms that are in that square root? Yeah, they both have this dx squared, right? I'm going to factor it out. All right, if I factor dx squared out of dx squared, 1 plus, and that second term, I think I'm left with this f prime of x squared. All right, kind of last two steps. I never, unless I try to get really creative on the Unit 6 test, I don't see differentials squared very often. I usually just see one of them, but since these two guys are being multiplied, the guy in the big parentheses and the dx squared, I'm going to separate that dx squared off and implement the square root on just that part. So I'm going to kind of split this square root here and square root this guy so that I have my big square root and a single dx, as dx being the square root of dx squared. Now, I've got a ds on the left. I got a dx on the end of my right. Anyone think they know what step we could do to get from ds to s? Let's slap an integral on both sides. So I'm going to write this in the formula. If you are not writing anything down, this is what you're going to want to write down. I'm also going to slap some bounds on this guy because just like the volume in the area we're finding, we want to find an actual distance here. So we will have bounds that we are going to employ. So what this is going to involve is essentially just finding a derivative and knowing a formula. I wanted to show you where that formula comes from because it's kind of a complicated one. So some negatives, I have to memorize a kind of complicated formula. Some positives, we're going to work with a formula that looks very similar at the end of the year with actually something Nate kind of touched on when we get to parametric functions, which are very much like vectors. It's super easy in calculus, don't worry. But where we split x's and y's, we're going to do something really similar. The formula looks really similar. Another plus for you guys, these integrals almost never come out nice. So the vast majority, like 99% of the time, you're not going to have to do this integral by hand. Okay. All right, I was going to make us do the next one by hand, but I think I might just have us plug it into the calculator. So this guy right here, I like to start, when we get any sort of weird formula, I like to start by using it on something where I can find the answer a different way. So looking at this guy, do I need calculus to try to decide how long this thing is, if that is a circle? No, what could I use instead? What the heck? Is he always in a place where he's getting in trouble?
Yes.
Okay.
You see him getting in trouble a lot.
Recently, he's been places that have been loud and rambunctious when they should not be. All right, so if I want to find the distance from here to here on that curvy semicircle, what geometry word comes to mind? Circumference. Anyone know the formula for circumference? 2 pi r. Now, I only want half this circle, so you guys cool if I divide this by 2? 6. All right, yeah, so pi r, what's r for this circle? 1. So when I finish this question, I better be getting the answer pi if we did our formula right. Now, this being said, I'm using this formula as a good example. Would I actually do the calculus instead of what I just did? Absolutely not. Yeah. Don't be sorry.
I know we learned this in like 5th grade.
Yeah.
I need a refresher. Like,
Yeah.
what is the exact definition? What is it? No, not the value. Like, what is
It's not a fraction, actually. It's a transcendental number, so it's not rational.
Why is value pi? Like, why is it used? Yeah,
It's this, it's
why
the
is
diameter of the string.
Yeah, it's like a ratio of parts of the circle to each other.
which part?
That's a great question.
Like, it's in every single
Yeah,
equation and it's constant. It's
it
never.
has to do with circles, and it like has to do with the ratio of specific things in the circle. It comes up so often that they gave it a name, kind of like E. I can get a better description later. Right now, I'd like to focus on the calculus if that's okay. All right. So, thing I notice is missing in this question. Anyone think anything's missing? All right. Bound, sure, might be able to get them from the picture. Something even worse. Yeah, we don't have a function. That's a problem. Anyone remember how to write the equation of a circle?
X minus a squared minus y minus a.
All right, we're centered at 0, 0. So let's go x squared plus y squared equals r squared, which is 1.
Wait, is it x minus a squared plus y minus a?
Yeah, if you
That's the
center,
center,
if you
right?
center it, something different. All right. The cool. Who? The pink kid? I'm not very scary though.
No.
No. All right. The cool part about arc length, I can actually do this formula. This derivative could be in terms of y or in terms of x. It works just as easy. I'm going to go ahead and work in terms of x because that's my personal preference. So I'm going to solve this for y. I'm going to square root using the positive root because we are above the x-axis with that semicircle. Note that I cannot write 1 minus x. It is not legal to square root both of those things. Please stop doing that. So let's go ahead to use this formula. Once we have an equation, really the only thing we need to find are a derivative and some bounds. So anything you want to tell me about this derivative? It's not that complicated. You've been taking derivatives for a very long time now. Chain rule. That's the thing I wanted to hear. We have a function inside another function. So I have the derivative of square root memorized as something over 2 root the inside. That's the 1/2 and the new -1/2 power. You take the derivative of square root a lot. It's nice to have it memorized. I'm going to put the regular inside function here. What is my derivative of my inside function? -2x. Technically, dropping the negative wouldn't be too bad here because I'm about to square this derivative, but better to be accurate. All right. So 1 plus derivative squared. So I'm just going to steal this derivative. I'm going to personally thinking about plugging it into the calculator or using it as I'm doing this by hand. I'm going to cancel those 2's. That's Wes Walker, isn't it? Nope. Well, I'm recording this and posting it on the internet, just using people's names. All right. What am I missing? Bounds. Thoughts on them? -1 to 1. We're talking the x to the left, the x to the right. Challenge question while we're sitting here. If I had chosen to work in terms of y, essentially I would have done exactly the opposite for the derivative. I would have solved for x and gotten it in terms of y. The derivative would look very, very similar. What would the bounds be if I were working in terms of y, though? Good. That would be weird, though. All right. Let's. That's for the equation of the circle. So x squared plus y squared is r squared. Back from like geometry. All right. Usually these. Oh, let's check to make sure this is pi. So we could use any calculator we want. I think I have Desmos open, so let's use it. Desmos. Yeah. Yeah. Radians is always the right answer, though. All right. 1 plus, what was it? Fraction, -x, square root, 1 minus x squared.
One is from the radius squared, right?
Which one?
The one under the radical.
Yes. All right. You guys recognize that number? Looks like pi. Yeah. Just to prove it to you that it's exactly pi. Oh, that's 0. Oh, whatever. Yep. All right. So this formula seems to be working. For the AP test, pi equivalent to 3.142, aka pi. 3 decimal places. All right, so usually that's kind of actually a harder version of this question because usually we're going to be given an exact formula, an exact interval to work on. So here's kind of an even more boring example. If we were working with this function, though, I do want to avoid kind of making my derivative harder than it needs to be. So here, how can I avoid doing some quotient rule here? What else could I write instead of x cubed over 6? for my like function to avoid quotient rule. Is that a question? Save those negative exponents for the second term. I could do this is 1/6x cubed, and then how could I use negative exponents in the second term? All right, I like x to the -1. I don't like 2 though. 1/2. We would need to keep that 2 on the bottom unless we went real fancy and did like a 2 to the -1. So here, really, you're just trying to maximize your time of not making your derivative hard. Here for my derivative, I'm going to bring down the 3. So 3/6 is the same thing as 1/2. I'll bring down the -1 and subtract 1 to get -2. All right. Yep. Really, this is going to be a battle of you versus your calculator. There are a lot of things that are kind of forgetful mistakes, I would say. Dropping the square root when you type it into your calculator is probably the most annoying one because then you have to retype everything. Also, dropping this squared, surprisingly easy to do. One thing you don't want to drop is your bounds. Thoughts on them? 1/2 to 2. They're pretty, I hate to use the word obvious because it was once used in a class for something that was not very obvious to me, but they're usually pretty in your face. Someone drew something on the whiteboard that was a matrix full of infinitely many infinite matrices and said, well, this is obviously the only solution. That is the least obvious thing I've ever heard in my entire life. All right, let's try one more. And then we'll talk about how is the AP test going to talk about you about this. Just for giggles, I'm going to do this one in terms of y, just to show you that it's just as easy. So if this is in terms of y, I want to solve for x here. Essentially, I'll square root both sides, but I want to write this with nice exponents because I'm about to take its derivative. If I want to write the square root of that cubed, 3/2, perfect. All right. Finding our derivative is not difficult. We're just going to do it like normal. I know, we've been doing too many integrals, right? We keep thinking about USA. All right. I'm taking a derivative. I don't really even have to worry about chain rule. The derivative of the inside is just 1 because we're taking the derivative in terms of y. All right. Let's set up. I got a whole bunch of stuff. 1 plus all this guy squared dy, because I'm now in terms of y. Thoughts on bounds? That would be great if I were working in terms of x. You got, yep. I got my other class too. All right, so you might be sitting here thinking, and I'll stand up for this part because this part's more interesting. You might be thinking these questions aren't very interesting. To which I would say I agree, they are not very interesting. Because they kind of come out and say exactly everything you need to do the problem. It's just not that thinky. So a few years ago, the AP test started using this in a new way that I think is a pretty cool question and has to do more with what we've been talking about with these regions that are bounded by specific graphs. And that is they've been talking about perimeter. It's a really cool question. So this one and the one below it are both from the past couple of years of free responses on these sorts of questions. Really love them. There's one on your problem set that looks very similar, but this would be a really good way to make one of these kind of rotations questions into a BC only question by making you do this because arc length is a BC only topic. So let's look at this graph. I'm going to do this one, and then I'm going to have you guys do the second one. I apologize, the second one's a little bit harder, but you'll be fine. Perimeter, so think of like circumference. You're going to stick a man right here, and you're going to walk him all the way around. the distance around your shape.
So should it be confusing?
No. All right, so we've got e to the 2x is this guy right here. It doesn't matter. I was just talking about the functions. Oh, yes. Sorry, the answer to your question is yes. Mhm. All right, so I'm starting. I'm only drawing there because I know what region I'm working with, but I'm bounded by the graph of this, the coordinate axes, so that's why I only started there. So that's the x and y axis. And then we've got this fun, fancy line, x equals 2. They're promising me that line is in the first quadrant by saying that k is greater than 0. So it's not going to be like x equals -1. So I've got this fun, fantastical region where I would argue 3 sides. Don't agree with fantastical? That's fine. I would argue 3 of the sides I do not need calculus to do at all. They are straight lines. I don't need calculus to find the length of a straight line. I'm going to label them just so we can talk about them easier. I'm going to label this guy A, this guy B, this guy C, this guy D. Which letter is going to need us to use calculus? D, because it's curvy. All right. Speaking of, how long is A? 1. It's exactly 1 because that is the y-intercept of that graph. How long is B? Let's go with the x value. Okay. That's at a specific place on this graph, but that's kind of just an example. The k could slide. And notice they want us to have our answer in terms of k, which means k is going to be in our answer. All right, and a creepier one. We're going from easiest to hardest. Before you answer, think about it. So give your count to 10. How long is C? I like it. E to the 2k. How do we get that? All right, here's our x value. This is on our function, so we're plugging k into that function. All right. For this vertical line, that's like the y value here, and we're looking for the y value on that graph. So we're taking our x value that we're at, plugging it into our function to get the y value. So I think this point is like k comma e to the 2k. All right, so we're like 3/4 of the way done. We have not done any calculus yet, though. So let's arc length S. 1 plus k plus e to the 2k. So I've walked 1 plus k plus e to the 2k. Now, I need calculus for the end. So I'm going to add an integral on. All right. I'm going to have a big old square root. Anything you know goes under that square root? Ooh. All right. I'm hearing this bold choice. Where's this coming from? Where's that 2? Derivative 2x. We still need chain rule. All of our derivative rules are still happening. I'm done, right? Down. Thoughts? Good. 0 to k. We still want to go from left to right. Our x values, 0 to k.
How would you plug that in?
We wouldn't because we don't know what k is. So notice it just says write an expression, not evaluate it. Good question, though.
So it's like this.
Yep, so that would be the end of the answer. Another way to ask that, sometimes you'll see the word integral put in there. So write an integral expression. But write an expression just means that's all I need. Write it. I'm done. Yeah. Yes. So eventually, if you could integrate that, this one would be a little nasty. I'm not really sure what method I would use. Probably some sort of trig sub. If you could evaluate that at the end, you'd plug in your k and plug in your 0. So that would be kind of a numerical value with k's in it. Yes, that whole integral is for d. So notice there's some parts of the question that are definitely easier and kind of in addition to your calculus. But if we're talking like me handing out points on this question, I would guess that this would probably be worth about 3 points. 2 of the points are probably coming from this integral. My guess would be 1 for the derivative, 1 for the entire integral, and then 1 for the kind of rest of the expression. All right, so I'm gonna have you guys end class today. This is the last question I want to do, so we'll end a little bit early, hopefully. This guy is a little bit different, a little bit harder. So let me give you some advice on how to attack this one. I would again split this into 4 parts. It kind of looks like 3, but it's going to be easier if you do 4. You have this guy here. I would cut this one at the x-axis when you think about it, because it's kind of applying to 2 different functions. And then here. All right. I would say there's one thing you have to do calculus on. There's one thing you could do calculus on. Thoughts on which one you have to? D. It's the curvy one again. So I'm going to give you a solid 5 to try to come up with anything you can. We'll go over it, and then I'm going to be done for today.
All right, the derivative in this one is definitely y. I'm sorry, a. A. Okay. You think C or that? Oh, did I get it? Wait, really? Yeah. That's what it says right there. So we're going to think of like all the volumes. So especially like this one, be careful if you're putting your x value in.
Or you can have them upside down and like this. That's what it looks like.
So we want to keep this distance positive. This is also not. It's a little bit high. So I think we want to do I think I'm tired too. All right, if you're saying C is 3, maybe rethink that.
X, U of X squared?
School wasn't 3, right?
Which is what?
A little less than 3.
Oh, so it's just E. Yeah, yeah.
I don't know. Oh, we can use my dragon here.
You're the one, right? Oh.
1, 2,
1, 2, 3. Is that a thing?
So there's not a thing.
Yeah, I saw that.
I think we're fine, yeah.
You could ask Pythagoras.
You guys decide on 1 and 2.
2 squared is
Yeah.
1 plus 4 is 5.
Yes.
Square root of
5.
No, that's you already did square.
You can do the art like formula for that one as well. I just kind of cute. Yeah, because you'd have the big square root.
That's 1 plus. The derivative square. Right. All zero. Oh, yeah.
Zero and zero to one. Goes like square root of 5x.
Never heard of 125.
It's 1 2 square root of 5. So.
That's what I said.
What?
One, I said square root of 5. I said square root of 5.
I said yes.
And then Sammy said, it's not just 1 zero to 5. It's square root of 5.
You're not fighting about your mathematics. What are you even doing?
Guys, how is she only E?
X 2x. Is it 2 E? X squared. I thought it's 2x E to X squared, yeah.
Well, that's equal to Y.
X squared plus 1 times E.
What's up, Kat?
I said square root of 5. No, it's just 5. It's square root of 5. I would have heard of 1 to 5 times.
I say,
Seven, 12, 13.
All right, let's see what we know. Anyone have any claims for any of the 4 sides? Raven. C is E. Now, how do we get C is E? Let's plug x equals 1 into this function. 1 times e to the 1 squared. That's all E. So C is E. That sounds weird. All right. Other claims. A is square root of 5. Now, this is the one you could have done using arc length. You could set it up because you have a function. You could do 1 plus derivative squared if you wanted to. What's a smarter way to do it? Just Pythagorean theorem. So you're talking 1 squared plus 2 squared is a squared. So a is the square root of 5. All right. Thoughts on, I'm guessing no one wants to literally list out what D is. So thoughts on B? 2. I like that you guys are saying positive 2. Be careful if you plug into that function. We're counting arc length as positive distance. So we don't want to use the negative 2 there. Kind of want to absolute value it. So let's set this up. I'm going to do 2 plus e plus square root of 5 plus. You guys told me I needed arc length, so I'm going to set up what I got. Thoughts on either the bounds or derivative? Bounds is 0 to 1. I like it. Any like nebulous, like overarching thoughts on the derivative? Product rule and a chain rule. So let's see if I can do this right. First, derivative of the second, chain rule, plus second, derivative of the first is 1. Cool? All right, this one says set up, then evaluate on your calculator. Did anyone do that? Neither did I. Equals a number. A positive number. No. I can look that up in a second. I don't know where my notes, I was just winging it today. I don't know where my notes went. So it'll be some positive number. I don't really know. I'm just going to cross out the directions and say set up. All right. But notice this one I could evaluate since I have no k's or any other like constant in there. All right, before we leave, I need to tell you some due dates and make a proposal for the test. Oh, I don't even have this in here. All right, I'm gonna write this down. All right, if you do not have a Unit 7 problem set, I would pick one up. I'm going to try to build in time at the beginning of classes to work on it so that I don't lie to you and say we have time when we don't. So bring that problem set the next couple of classes so I can make sure that I give you some time. I would like to propose the problem set be due on, do we have school on Monday?
No.
Tuesday.
No. Is it the 23rd? But it's
The 22nd.
Oh. Oh, yeah, we start on that.
So 2/22, 1 week from today. Again, I'm going to build in the time at the beginning of class to make sure that I give it to you. So please bring this problem set. You'll have now you got 2 classes to work on it? One class to work on it, and maybe I'll build in some time at the beginning of that 2/22 class. So I'll build in probably half an hour next time, half an hour of class after that. Test will then be 2/24, Thursday of next week. Proposal number 1. You get a buddy, partner test. Proposal number 2, semi-mastery test, but not in the way we've done it before. So mastery test was the one where I went around and checked it for you. That's a little stressful, especially with these, because me and my eyes with all of those integrals is going to be a little bit challenging. So what I propose I'm going to do, if anyone was in my class last year in AB, it's going to be very similar how we worked the notes checks. So I'm going to build a Desmos form. Let's say we have like 1, 2, 3. There's going to be a box where you can put your numerical answer. If you put the right answer in, it's going to be like, oh, correct. And if you don't put the right answer in, it's going to be like, hey, try again. So you'll have a way to check those numerical answers. If there's any questions where it's like a setup but do not evaluate, I'll come around and check those off. Does that make sense as a proposal? Yes, you'll get to work with a partner, and I'll have you submit your work just so I can check for notation. Yeah.
What if we get it wrong?
If you get it wrong, I'll give you some partial credit.
Like our notation, but we still get the answer.
So that I'm going to be walking around also with an answer key, but just so I don't have to like go around and check off all the correct answers, it'll let me kind of check those notation things. No, Hefty chooses partners.
So what's the difference between the 2 options?
There aren't 2 options, there's just one.
Oh.
You get both. You get proposal part A, proposal part B. Full proposal, all of that.
The partner, are you mix up like similar grades?
Yeah.
Probably, but I'll probably mix it up so that if I remember you were partnered, I'll mix them up from a little before. All right, proposal accepted? Cool. All right, we have 7 seconds. Have a lovely couple of days. Bring your problem sets next time. Bye.
Wait, Sean's not group, right?
I wanted to go home.
It's just downstairs where you're.
I gotta go home.
My dad's gonna be late anyway.
And the other partner class is that instead of you checking it, Desmos.
Yeah, so what it's going to do, these take a really long time for my eye to check all of it. So what it'll let you know is like if your numerical answer is right away, and then at the end, if you want me to check over notation, I can.
Okay.
So it's just going to let me walk around and help a little bit more.
Okay.
Is what I'm hoping.
Okay.
We'll see. I haven't done one like this before. You get to be my guinea pig. All right. I got a dog that needs attention. See you, Nazi. Who is that? Oh, I don't know. Oh, wait, let me see now.
They say right there.
how do you spell the last?
Wait, is the other work?
The one with the fly over
What unit are we on?
I mean,
Is he actually good?
I don't know if I'm
No. What is it? Whoa.
Yeah.
Why?
You know, we sent the new year that.
So wait, does that mean that the awards assembly has to be?
That's lovely, thank you.
Okay.
Yeah, so I think that's been maybe Friday, 4 o'clock.
Or the COC meeting,
Okay.
I can speak earlier.
Yeah, dude,
It's calculus, none of us are in the same place anyway.
right?
Oh man, alright, I gotta. My dog needs me, I'm leaving. He's traumatized by doggy daycare yesterday. He won't go up the stairs or down the stairs without rides right now. Like his little body's just sore. So, we go 10 minutes.